Okay, so good afternoon, everyone, and welcome to the PhD defense of Gaëtan Abeloos, which is entitled Control-Based Method for the Identification of Nonlinear Structure. So my name is Abeloos, and I have the pleasure to chair the jury. So the defense will be organized as follows. So we have first a presentation by Gaëtan. We summarize the main results, the main outcome of this research. Then we have a lot of questions and discussion with the jury members, and then the deliberation. And so we look forward to your talk, and now the floor is yours. I will make the introduction of the jury just after the presentation. So let's wait a little bit. So we can start, and we look forward to listening to your talk.
Et bonjour à tous et à toutes, bienvenue à cette définition de thèse. Elle se fera en anglais, puisque tous les membres du jury ne parlent pas français. Donc, je vous souhaite d'ores et déjà une bonne présentation. J'espère que ce sera chouette et agréable. Hello everyone, welcome to this thesis defense. I'm really glad to see you all. Thank you all for coming, and especially the jury members for your time, and the ones who came from abroad, especially. Today we'll talk to you about a set of methods that are used in experiments in structural dynamics to identify nonlinear systems. These methods use feedback loops and feedback controls, and so they are called control-based methods. When I talk about structural dynamics and experiments in structural dynamics, I, of course, talk about structures. And so this is an example of a structure, a nice satellite, and we are interested in how the structure will behave in its environment. And so we will interrogate the structure using a tool called an actuator that will push and pull on the structure. We can push and pull in different manners. And in this presentation, I will talk about an excitation at a regular interval. So a periodic excitation. Push and pull at regular intervals. That is nice because we can test one amplitude and one frequency at a time. We will then measure the response using a sensor and record the response signal. And so here is the diagram of what I will call an open loop experiment. And it is just a little engineer that chooses an amplitude and a frequency, and that will define the excitation signal. We apply this excitation signal onto the structure and measure the response. Let us imagine a first experiment. In this experiment, I will push and pull on the structure at regular intervals, and I will measure the response. This is the first step of our experiment. Then I will increase the amplitude of the excitation and measure how the structure reacts to this change. And intuitively enough, the amplitude of the response increases as well. And then in the first step, I will decrease the amplitude of the excitation back to its initial value. And in this example, the response goes back to the initial signal. So we are exactly like we were in the first step of the experiment. We can graph and display these experiments on a diagram to illustrate its results. And so here on the right, we have a diagram that links the excitation amplitude with the response amplitude. So you can see we began here on the lower left corner. Then we increased the excitation amplitude, and then we saw the response amplitude increase with it. And then we decreased the excitation amplitude, and we went back to the initial position. We can notice that this diagram is a bit boring. It's a straight line. And that's because our structure behaved linearly. And that's an assumption we often take, that the structure behaves linearly. And we are not obliged to stay at constant frequency and modify the amplitude. We can also stay at constant excitation amplitude and modify the frequency. And this curve is a little bit less easy. You can see it's not a straight line, but it is very interesting because we can see that at a specific frequency here, there is a large response amplitude. That's what we call a resonance peak. Okay, now let us imagine a second experiment on a different structure. As we did before, in the first step, we push and pull on the structure at regular intervals and measure how the structure responds to this interrogation. And then I will increase a tiny bit the excitation amplitude. And this tiny change will result in a huge change in the response amplitude. You can see that for a tiny change in the input, there is a huge change in the output. That's what we call the jump phenomenon. A small change in the input means a large change in the response. And then even weirder, if we go back to the initial excitation amplitudes, if we go back to the first step here, well, the structure will stay at high amplitude. And so we have a weird phenomenon where we have the same inputs, but a widely different outputs, a widely different response. That's what we call the folding phenomenon. And we can do exactly the same as we did before and illustrate these new experiments in a diagram that will link the response amplitude to the excitation amplitude. And at small amplitudes here, in this example, where it's very similar to the linear case, we increase the excitation amplitude and response amplitudes increase. But at this point here, there's no more response on the right. That's what we call the bifurcation point. And that means that if we increase the excitation amplitude further, well, the structure will jump to another branch of response. In this case, a higher amplitude branch of response. That's the jump phenomenon. And if we go back and decrease the excitation amplitude, well, the structure will stay on the higher branch, and so we have different possible responses for the same input. That's the fold. And we observe something similar if we keep the excitation amplitude constant and change the frequency. We still have a resonance peak, but this time it skews to the sides. And that explains why we can have bifurcation points here and folding. And now these different branches are not disjoints. That's why I put a little question mark. They're actually joined by another branch of responses. So we have three different responses for the same input. And this particular response here are unstable. The structure hates them and wants to leave them as soon as possible. And so this leads us to the questions and the objectives of control-based methods. In general, in a broad sense, we want to know how the behavior of the structure evolves with amplitude, with different loading cases. And specifically, in this case here, we ask ourselves how many responses are there? In this case, there are three, but are there more? How can we know? How do we choose which response we identify during our experiments? How to reach them individually? And finally, this response here that the structure hates, how do we observe its experiment? And this presentation, to answer all of these questions, will be separated in three poles. Each of these poles is a different method. We have two here already existing control-based methods. One is called phase-lock testing, and the other one is control-based continuation. And then I will add to the mix the method called adaptive filtering, which is a signal processing method. In the first part of the presentation, I will analyze how do phase-lock loop and control-based continuation tackle the two challenges. How do they tackle folding, and how do they tackle instability? Then I will couple phase-lock loop testing with adaptive filtering. We will see how the performance of the phase-lock loop increases. Then I will couple this time control-based continuation with adaptive filtering, and we will see how this opens the door to online control-based continuation. And finally, the last part, I will couple every method together and create one method, and we will see what problems this new method can tackle. So this is the outline of the presentation. Is a bit of like a Venn diagram linking different methods together. And let's begin with control-based continuation, the first control-based method that we present. The origin of control-based continuation is a bit complicated, so I'll simplify it for you. But basically, we want a new perspective in our problem. We want to solve folding. For that, we look for a new point of view. And I take back this curve that links the excitation amplitude with the response amplitude at constant frequency. This is called an S curve for obvious reasons, I think. There's something really peculiar about this curve. Each point here is a different response, and each of these responses has a different amplitude. And the contrary is true as well. If we can impose the response amplitude, we will have one and only one response that corresponds. And that's the opposite of folding. So by imposing the response amplitude, we can solve the folding problem. And so this time, our little engineer will not choose the amplitude or the frequency of the excitation. They will choose the amplitude frequency of a reference signal. And then we compare this reference signal to the response that we measured. And so this act of taking the response back here is called the feedback loop. And this comparison here will be fed into a controller, and it is the controller that generates the excitation signal. Now, this is a strength and a weakness, because this feedback loop here is a dynamical system itself. It has its own behavior, and the behavior is different than the structure alone. That's good, because it will allow us to stabilize the responses and unfold the curves. But it's bad, because we are only interested in the behavior of the structure, not the behavior of the feedback loop. And so we will have to do additional work to ensure that this feedback loop behaves exactly like the structure of the loop. But I will talk a bit more into detail. So, how and why control-based continuation stabilizes and unfolds a frequency response curve with the resonance peak here? Well, the nice thing is that this feedback loop behaves like like an oscillator as well. So it's exactly like before. We have the different frequencies, different amplitudes, and there is one particular parameter of oscillators that is very interesting. This is damping. You have to know that if you increase damping, this resonance peak here gets flattened. And if we increase damping enough, it gets enough flattened that there's no more folding and no more unstable responses. And thankfully, the controller can modify the damping of the feedback loop. And so we can design a controller that will ensure that there's no more folding and no more unstable responses. Now we have an experiment with a good controller that stabilizes our structure. And we have two input parameters. We have the reference frequency and the reference amplitude. And in this visualization, each coordinate here corresponds to one set of input parameters. And we don't know in advance the resulting excitation amplitudes that will be generated by the controller. That's why it's useful to draw it like this. If I'm only interested in the responses at constant excitation amplitude, I will have to find this path, this complex path in the input parameter space. And I don't know it in advance. And so the state-of-the-art of control-based continuation relies on iterations. I can try something, it will be wrong. I will correct it, then try the next one, it will be wrong, then correct it. And so it's an iterative process. Thankfully, because there are only two input parameters, it is a plane. The input parameter space is a plane. And so I can actually have a simpler continuation process that scans the whole image, that scans the whole input parameter space. And so one of the ways to do this, one easy way, is keep the reference frequency constant and increase the reference amplitude. So we then change the reference frequency. So we will identify multiple S-curves at different frequencies, and this should give us an idea of the whole response surface. We can do something similar by keeping the amplitude constant and varying the frequency, then trying at a different amplitude. And that's very close to something that exists in the literature as well, called response control testing. So these continuation processes are much more simple, much simpler. But the drawback is that we have to identify responses outside the scope of interest. These responses are at really high excitation amplitudes. So that can be a problem. And then in post-processing, you have to extract the results we are really interested in. And just a comment, you can do the same locally. You can identify the surface locally, and that can help you draw your path in the space. Good. As we here, I have a revelation to make. I've not told you the whole truth or showed you the whole truth. I've always shown the response as a sine wave. Well, reality is not as simple as that. If the excitation signal is a sine wave, the response is in general not a sine wave. It's not always periodic either, but we will focus on periodic signals. But you can see it's more complicated than a sine wave. It is actually a combination of multiple sine waves called harmonics. Each of them has different amplitudes and a different frequency. Now that's a problem for our little feedback loop here, because remember, we have the reference signal here. We like simple things, so we define it as a sine wave, and we compare it to the response that we measure, which is itself multi-harmonic. And so these higher harmonics here are fed back here at the input of the controller. And so the controller will increase or keep or modify these harmonics, but they will be still present in the excitation signal. And our objective of exciting our structure with a pure sine wave is not accomplished. How will we solve that? Well, with another feedback loop. If we take the response and somehow successfully isolate the higher harmonics, we can remove them from the input controller. And so we have a pure sine wave here, a pure sine wave here, and we are exciting our structure like we want it. I will go into more detail on how this works. But now we can do the summary of the state of the art of control-based continuation. It's a really powerful method. Here I've only talked about oscillators, but you can actually use it on different types of systems. But in the case of oscillators, you still need to ensure that the S-curves here are monotonous, meaning at constant frequency, every response has a different amplitude. The control is not meant to reach a target like in traditional feedback control. It is meant to change the dynamics. And then we need to iterate on the reference until we reach the excitation that we want, the right amplitude and the right frequency components, the right harmonics. I will illustrate now these control-based methods on an experiment. So this experiment is composed of a thick frame here. That's not the structure. That's just the support of the real structure that interests us. This is the thin beam here. The particularity of this thin beam is that it's slightly curved. So there is a radius of curvature, and that makes this beam have a nonlinear behavior. We will excite this frame from the bottom and measure how the beam vibrates using a laser. If I do the continuation process that I talked to you about, I keep the frequency constant and I increase the response amplitude, I will identify an S-curve. And if I identify multiple S-curves here, I will have rips of the response surface. And so I just have to merge them together to approximate what is the real surface here. And once I have done that, I can slice this surface of constant excitation amplitude, and I will have a frequency response curve. And this is the one with the resonance peak, remember? And so this is the real thing that I want to try. Okay, now let's go to phase lock, the second method. Once again, I've not told you the whole truth. I've talked about the amplitude of the response. I've talked to you about the higher harmonics, but there's one more parameter that you don't know about. You can see here in these two examples, the amplitude of the response is exactly the same, but the signals are different because one has some lag, it's shifted in time. And that's a very important parameter that's called the phase lag. And drawing here the relationship between the amplitude and the frequency, the graph, the phase lag of the responses. And once again, here across the resonance peak is monotonous. It only drops. And so we can draw the same conclusions. If each of the responses has a different phase lag, if we successfully impose the phase lag, then it will correspond to one and only one response. And so we can solve the folding by imposing the phase lag. And that's exactly what we are going to do. So we'll take back the diagram of the open loop experiments. The little engineer here beforehand, in the open loop system, it shows the amplitude and frequency of the excitation. In this case, we will only choose the amplitude and not the frequency. And the frequency will be modified by a controller. So we'll feed back the response, estimate the phase lag, and the phase lag will be input into a controller. And now the job of our little engineer is to choose a phase lag target. And we'll compare the measurement of the phase lag to the target. And the controller will correct the frequency until they are both the same. So this is more a traditional feedback control. Another big question is, okay, we have a mechanism to reach the appropriate phase lag, but can it identify unstable responses? Inside the controller of the phase lock loop, there are parameters. In my case, I've chosen to use a PI controller. It has two parameters, integral gain and a proportional gain. If both of these are equal to 0, well, the frequency is left alone. It's kept constant. And that's exactly the open loop system. And so an unstable response of the open loop system will be unstable. And that's what the white color signifies. But if we increase the controllers, we can arrive in the color field here. And that means that the phase lock loop is stable. So you see, it depends on the controller gains, whether the phase lock loop is stable or not. And something very important is that in yellow here, you are at the verge of stability. And in blue here, you are comfortably stable. But you can see there's a minimum point here. There's an extreme. It's a point where the performance is maximum. You cannot go better than this. And so the performance of the phase lock loop is constrained by the system you are studying. And another thing to notice is that if the phase lag estimation slows down, the color field here shrinks a lot. So that means that the phase lock loop is a lot less stable. And so it's very important for the phase lock loop to have a fast phase lag estimation. And this brings us to the summary of the state-of-the-art phase lock loop. It's a very, very strong method because its parameterization of resonance is really natural. It's really natural to parameterize a resonance peak through phase lag. And so the resonance can be identified really straightforward. But this strong point is balanced by three drawbacks. The first one is that it's constrained around a single resonance mode. Like I said, the performance is limited by the structure you're studying. Can go much faster than the structure you're studying. And slow phase lag estimation can render your phase lock loop unstable. I will illustrate this using another system. It's a bit of a peculiar system because it's a hybrid system between physical and numerical. So we have a metal beam here, which is fairly physical, fairly material, but it's mainly linear. And so I will add to this beam an artificial nonlinearity. To do this, I will measure the displacement and the velocity of the beam. I will apply a nonlinear function to it numerically, and I will input the signal back into the actuator as a force. So we have a force that depends nonlinearly on the displacement, that's nonlinear stiffness, and a force that depends nonlinearly on the velocity, that's nonlinear damping. So you can choose the nonlinearity that we apply to the structure. Using a phase lock loop, I set the phase lag to identify the resonance. And we can identify this gray curve here, which is called the backbone. This is the collection of every response at resonance. And it's very easy to do this with a phase lock loop. You just keep the phase lag at a certain value that corresponds to resonance and increase the amplitude. If you do the contrary, you obtain the resonance peak here. You keep the amplitude constant and you vary the phase lag. And until now, this is what we did with phase lock loop. We identified fundamental resonance. But now you know that there are more harmonics than the fundamental harmonic, the first harmonic. And okay, the first harmonic can enter into resonance, can have a resonance peak. And that is accompanied by a drop of pi radians in its phase lag. But what happens in the higher harmonic? In this example here, there is a third harmonic. And you can see that the fundamental peak is found back in the amplitude of the third harmonic. And this is accompanied by a drop of 3 pi radians in the phase lag. But that's not all. There is a second peak here that is absent from the first harmonic. And that's when the third harmonic resonates. And that's what we call superharmonic resonance. And it is accompanied by a drop of pi radians in its phase lag. And it can be problematic that there is an influence of the fundamental peak on the third harmonic. And so I showed that we can remove this influence. If we combine the phase lags we can transform the third harmonic phase lag, and it only drops the value of pi radians as the super harmonic resonance. And we can use that with the phase lock loop. And this is the things we can obtain. If I focus here on the left, I have a third super harmonic resonance in my system. And by setting the phase lock loop to target the third harmonic phase lag, I can identify the resonant response here in the backbone curve. And I can also identify the resonance peak around this backbone. But if I try to do the same with the fifth superharmonic resonance, there's a problem. You can see it looks really weird. There are three disconnected lines, and the fifth harmonic at this point here is not high at all. And that's because of the influence of the fundamental. And so we can remove the influence of the fundamental, like I showed you. And if we do this, we have a very, very clean backbone curve. Great. Now we can go on to the third method that I will present. It's adaptive filtering. And that will explain how these two mystery boxes work in the two control-based methods. In phase lock loop, we have the mystery box that estimates the phase lag. We don't know how, but it does. In the control-based continuation, we have a mystery box that isolates higher harmonics. Well, in reality, behind these two boxes are the same process. It's called Fourier decomposition. And Fourier decomposition means identifying the Fourier coefficient. Basically, what we want to do is identify the amplitude and the phase lag of each harmonic. And there are multiple ways of doing this. One of the ways, traditional way, we say, is performing some operation on the signal that we are interested in to transform into something like this. And what is interesting about this signal here is that it's not centered on zero. Here, the center is above zero in this case. And this value, this shift, is actually the Fourier coefficient. And one way to identify it is to integrate over one period. If we do this, then we have the Fourier coefficient, and we can identify the amplitude and the phase of the signal. It's very accurate, so that's why it's a traditional way of doing the Fourier decomposition. It's very fast. After only one period, you have a very accurate estimation of the Fourier coefficients, and it's just a mathematical operation, so it's really stable. The problem is that it's an infrequent. You update your Fourier coefficient estimates every period, and that's not fast enough for the phase lock loop. And so with the phase lock loop, we use a different method. We still want to identify this non-zero mean here, and we will do this by filtering out the oscillations. If we filter out the oscillations, we have a signal very close to this middle point here. And the low-pass filter that we use is not perfect. That means that we don't filter every oscillation. There's a pollution at steady state. And if we want low pollution, high accuracy, then the filter becomes really slow. And we've seen that it's very important for the phase lock loop to have a fast phase lag estimation. And so if you want a fast phase lag estimation, then the pollution will be very high and the accuracy will be very low. So there's a trade-off between accuracy and speed. But it's very frequent. The estimate is updated continuously through time. So it's very adapted for phase lock loop. And it's very stable as well because the filter is very simple. Now let me introduce to you a new method. It's an existing method actually, but it's newly adapted to control-based methods. It's called adaptive filtering. The main goal of the adaptive filter in the literature is to take a reference signal here and make a copy of this. We want to clone this signal by using a set of input signals. And so we scale these input signals by weights and combine them together. And this will be our synthesized signal. Then we compare the synthesized signal to the reference signal, and an algorithm will update the weights so that these two signals are as close as possible to each other. But I'm not really interested in that. I'm not interested in the synthesized signal. What interests me is that if in the input signals you have sine waves, then the weights are the Fourier coefficients you are looking for. And so it's an emergent use of adaptive filtering where the outputs are the weights of the adaptive filter. And what is the result?
you have a signal and you want to estimate its amplitude or its phase lag. Well, you put it into an adaptive filter and you take back the weights. And you have very fast a good estimation of the Fourier coefficient. The accuracy is very good. In theory, at steady state, there is no steady state error. The speed is really high, and the frequency of the updates is really high. Now the problem is that the adaptive filter is a dynamical system. And that means that if you put it into a feedback loop, it can be unstable. And if you have an unstable adaptive filter, you can make it stable by sacrificing a little bit of speed. But the speed is still much higher than the one of synchronous demodulation, for instance. Let's compare them with a simple numerical example. I have a sine wave here, and I want to identify its amplitude. If I use the Fourier transform, you can see that this curve is only updated once per period. So it's very infrequent. But after only one period, you have a very good estimation, very accurate estimation. Now with synchronous demodulation here, you can see it takes more time to converge. It takes like 3 or 4 periods in this example. And you can see that at steady state, you have this pollution, you have this oscillation at the end. And if you want to remove this oscillation, that you will take much longer to converge. And that's a problem for phase lock loop. And if you want to go fast, then you will have an even greater oscillation area. For the adaptive filter, you can see that it's continuous runtime as well, or rather, it updates every time sample. But after one period, we have a very, very good estimate here, and there's no statistic. Now, what happens if you link adaptive filtering with phase lock loop testing? What happens in this case? Well, I can already tell you that the accuracy of the phase lag estimation will be improved, and that will improve the accuracy of the method as a whole. And even better, the phase lag estimation will be faster, and a faster phase lag estimation means a more stability. The phase lag will be more stable. Now the problem is that there is a potential instability in the adaptive filter. So once again, you can sacrifice some speeds to increase stability. And I will illustrate what I just said by introducing a new experimental setup. It's a really, really thin beam. It's almost a sheet of metal that is clamped at both ends. And I will push and pull on this beam with my actuator. And because it's so thin, when it deflects, it will enter into tension. And that's a geometric nonlinearity. And you will see that it causes nonlinear effects. And even worse, it's really sensitive to the boundary conditions. And when I put the setup together, I accidentally put some pre-stress in it. You will see it will generate really peculiar nonlinear phenomena. But at first, let's stay simple. I just want to identify a branch of unstable responses. So we will start at the top right corner, and we will try to identify this branch. And if I use Fourier transform that updates once per period, it works well in the beginning. But at some points, the controller will correct the frequency, and it will overcorrect, because it's not frequent enough. And so it will overcorrect again in the other direction, and we will lose stability because the estimation is taking 3 things. With synchronous demodulation, you can already see that the line is thicker, and that's due to the inaccuracy, due to the oscillation that's left after filtering. And if you try to identify this branch, at some points, the filter is not fast enough to ensure that the phase lock loop is stable, and so we lose stability. If we want to increase stability, increase the speed of the phase lag estimation, we would have an even thicker line. And finally, let's see adaptive filtering. The accuracy is pretty good, so the line is pretty thin, and it's fast enough that we can keep stability all along the unstable branch. Okay, that was phase lock. Now let's link adaptive filtering with control-based continuation. What it allows us to do is a continuous Fourier estimation. Before, we had to update the Fourier estimates, and we had to update the higher harmonics that were separated, remember? But this time we can do it continuously. That means that we can cancel the higher harmonics in the excitation automatically, continuously through time. And that's a method that I call online control-based continuation. And it opens the door to a really powerful piece, is to sweep the input parameter. Before, we had to go step by step, and now we can continuously change the input parameters of the control-based continuation. Let me show you examples of what online control-based continuation can achieve. I will take back this artificially nonlinear setup, and I will do like I did before, scan the input parameter space. I will identify successive S curves at constant reference frequency, and then I will do this experiment again and again to have different S curves at different frequencies. When I extract the frequency response curve, I get something like this. First, this orange and blue curve here are open loop experiments. So this is what I talked about in the introduction. And you can see you have jumps here, there, and there. And that was the problem of open loop experiments. In yellow here, you have the offline control-based continuation, the state of the art. And to compare to this, so this used Fourier transforms to update the higher harmonics. And in green here, it's almost indistinguishable. This is the online control-based continuation, but did that work step by step. So it's almost the same, but it's already faster. But we can do better. With online control-based continuation, you can do parameter sweep. So it's similar to a swept sign instead of a stepped sign. And you can see that it's much, much faster because I chose a sweep rate much, much higher. And you can see that we do sacrifice some accuracy to the benefit of speed. Another way of using online control-based continuation is to use different continuation processes. The arc-length continuation process is taken from numerical continuation, and I have adapted it to online control-based continuation. If you already know one point on your curve, you know that if you draw a circle around it, there are only two intersection points. The previous points that you already identified, the next points. And so what you can do with online control-based continuation is progressively open up this arc angle until you detect that you cross the curve that you want to identify, and then register this new point. And that's a really, really simple method to implement, and it's really fast. The advantage is that we stay in the vicinity of the curve that we have to identify. It's really well adapted for identifying frequency responses, and it works on multiple degrees of freedom. To illustrate this method, I will take back this thin beam setup, and we will see the exotic nonlinear behavior that I talked to you about. At some excitation amplitude here, you can see that the resonance peak has a weird appearance. You can see here a peak that is mostly familiar, but there is a loop here that's completely detached from the main curve. That's what we call an isolant, or an isolated response curve. When we increase the excitation force, this isolant grows until it connects back to the main branch there. And you can see that these curves were identified experimentally using the arc-length continuation procedure. You can see that it can handle very well complicated topology, like multiple inflection points, and identify a closed loop. And the last method that we talk about is another use of online control-based continuation. And this time, spoiler alert, it will be combined with phase doctrine. Let's go back to the diagram of the control-based continuation. So our lead engineer chooses the reference, and we have the closed loop of the control-based continuation. But this time it's an online control-based continuation. That means that we can change the amplitude and the frequency continuously through time. And so the lead engineer doesn't have to choose a frequency anymore. It can relegate the task to a phase lock loop controller. And so we have the phase lock loop here, in addition to the control-based continuation loop. And so we take the response, estimate its phase lag, and put this in a controller. And it will be the job of this controller to change the frequency of our reference. And that's thanks to the online control-based continuation, allowing us to change the frequency in a continuous manner. Now, why is that useful? I will take finally again this thin beam setup because it's really nice. And I will show you that, like, remember, like here, the frequency response curve. You have in light gray here the main branch and the isolated response loop here. And on top of that, I've drawn the backbone curve of this resonance. So this is the collection of every response at resonance. And you can see that at this excitation amplitude, there's not only one response at resonance, there are three. One at the resonance peak of the isola, one at the reverse peak here, the other end of the isola, and one on the main branch. And that can be this diagram on the right here that links the excitation amplitude to the response amplitude. So it's similar to an S curve, but that has constant frequency. These are all responses at resonance. And you can see that for a particular excitation amplitude, you can have three different points of resonance. And that's a problem for phase lock loop. Because phase lock loop uses the excitation amplitude here as an input parameter. So if we begin here, and we increase the excitation amplitude with the phase lock loop, we will reach a bifurcation point and we will jump to higher amplitudes. And the nice thing about control-based continuation is that you don't care about the excitation amplitude. It's decided by your controller. And so if you use the response amplitude as an input parameter, you can identify directly every point on this folded backbone. Great. So the summary of this method that I call control-based phase lock loop is that it takes the best of both worlds. It has this high stability and high damping thanks to the control-based continuation feedback loop. But it has a really powerful parameterization of resonance of phase lock loop. And so it's really easy to track the resonance of an oscillation. It's really adapted to identify backbone curves. And it can handle weird nonlinear phenomena like isolas, model interactions. So this brings us to the conclusion of this talk. This is a summary of the contributions that I've brought. I've studied the two existing control-based methods, and I've seen how they tackle folding and instability with a general nonlinearity. I've used a phase lock loop to identify superharmonic resonances experimentally, and I have introduced adaptive filtering as a way to perform online Fourier decomposition. This allows to increase the stability performance of phase lock loop. And this opens the door to online control-based continuation. For online control-based continuation, you can have new continuation processes like the arc-length control-based continuation. And then you can combine control-based continuation with phase lock loop to have the control-based phase lock. How is that useful in the industry, for instance? This is a diagram I've taken from an article about Thesis. And it represents different methods that are used in ground vibration testing of aircrafts. On the left here, you have broadband excitation methods that are really fast because they can identify multiple modes in a single experimental run. The problem is that they rely on linear assumptions, so they cannot be applied on nonlinear systems. On the right here, you have the method that is usually used in case of nonlinear resonance. It's called phase resonance appropriation. And we have to tune the frequency, sometimes manually, to find resonance, then increase the amplitude, then tune it again. And every time you have to wait for the transients, the natural transients of the aircraft to be damped up. So it takes a huge amount of time. And after this thesis, I propose two complementary methods that can be used in these contexts, for instance. If you're interested in the nonlinear frequency response of a system, of a multi-mode system, you can use control-based arc-length continuation. And if you want to identify a single mode, you can use control-based phase lock loop. Both of these methods are quite simple to implement and to apply. the number of parameters is not astronomically high. They're reliable and robust because they tackle very efficiently folding instability. They are very fast thanks to the control-based control loop that increases damping. So you don't have to wait for the structure to naturally be damped out. Both remain in acceptable levels, and they are exhaustive, so they can identify really advanced nonlinear behavior. And these nonlinear behavior are indeed observed in the industry as well. This is an example of a test that was done on a tail plane of an Airbus A320, and there was a modal interaction between this node here and this elevator node. And so it's very important for the industry to have tools to tackle these complex phenomena in an acceptable amount of time. And I hope this thesis brought us closer to industrial application of control-based methods. Thank you so much for your attention. If you have any questions, I will be happy to try to answer.
Is to assistant member of the
a traditional way of doing this decision to multiply the ones by a sine wave because of the coefficient. That means that the only non-zero here is the one at this frequency. So if you take a single sine wave, you have a sine wave that lasts twice. So the oscillation will be
mentioned that if just input just to include that's
divergence in these changes. So this is you have the appendix of the dynamics of the picture with the time of convergence. That was only considered at the frequency of interest. But of course, if you choose an input signal that's at different frequency, then it will converge take longer to converge. So in the thesis, you can plug in the frequency difference than the one of the input, so the reference signal has a frequency difference than the fundamental, we will see that either the RF filter is overdamped or underdamped. So my answer to your question is it sufficient to only the fundamental? In my experience, yes. But if you are particularly interested in fast versions of the frequency, you should consider this frequency as then consider subharmonics. Imagine here it's the fundamental frequency. Here you have half the fundamental.
Those components also contribute to those constant. Related to very thin so this very isolated response regime. And my question is actually what would be the dynamic or physical force for
so this definite explanation, no, but I suspect it is a modern interaction. And I have two things that lead me to that hypothesis. That first, the harmonic contours of the second harmonic was really high. So I suspect a 2-to-1 modern interaction. And the second thing that gets me to this conclusion is that the folded backbone curve, the other folded backbone curve that I encountered was in the case of a modern interaction as well, the 5-to-1 modern interaction.
Do you recall the frequency ratio between the, was there an associated method twice the frequency that you analyzed? Was there some natural frequency?
This is the thing I wish I checked, but I haven't checked. So this is a hypothesis, but it's not confirmed.
Yes. Thank you for your explanation there. Then my next question would be that yeah, in fact, you placed a strong focus, which is very useful, I think, for the context of the previous and our methodology to periodic responses and in particular to harmonic excitation. Could you somehow provide some justification why it makes sense to actually look into harmonic excitation from an engineering perspective?
Yeah. The main motivation behind considering only harmonic excitation, and they are true. First one is simplicity. If you have to choose multi-harmonic excitations, then you have a whole bunch of dimensions of input parameters more, so it's more complex. And the second one is the proximity to a test that is used in industry, which is simply a certain sign or step sign excitation. And to get really close to what is already used in the industry, well, it's sometimes easier to do something similar, and that is harmonic excitation.
Okay, so you mean the link between what's typically done in testing, so in order to validate or identify a model that makes sense. That's right. Yeah. Then my other question is related to the situation that in linear vibration analysis, you take special care to identify just the dynamic properties of the structure on the test and be very sure that you don't obtain significant sensitivity to the excitation method that you are using. And in your particular study, very often you define the system boundary in such a way that you include parts of the excitation mechanism, say sometimes even with complete exciter, so that you said input is the voltage into the shaker, sometimes the coil, let's say. Could you comment on this? And in particular, I would be interested perhaps, and sometimes this might not be a limitation. So maybe in other words, can you design, or how would you design a test grid so that it doesn't make a huge difference? I'm still rather open about questions. Take your time.
If I knew a way to ensure that the force that I apply to my structure is exactly the force that I want to apply to the structure. I think I could patent that to be very rich, because I think that's an open problem in the field, like structure, shaker structural interaction. That's a really difficult problem. And that's one of the motivations behind the design of the artificial setup, is to indeed ensure that the nonlinear force is the one that actually apply. And in this work, I've not put focus on ensuring that the force that I apply on the real structures is indeed the force that I want to apply. So that's why in these systems, the input, the output of the loops is always the voltage, and not the force. And I deem this acceptable in the work because it really compares open loop experiments with closed loop experiments. And if there is interaction between the exciter, the actuator, and the structure, it will be present in the open loop system as well. And so if you successfully solve this interaction between the exciter and the structure in the open loop tests, then there's no reason why you shouldn't successfully apply it in the closed loop as well. So the focus here was really to make correspond the open loop testing with the closed loop testing. And then over that, on both subjects, you can focus on this problematic. And so I don't know if that's a satisfactory answer.
To some extent, yes. On the other hand, I think open versus closed loop also, I guess you could try to define the force as the input to apply excitation. And I mean, you are certainly aware of the frequency that even if you just attach a shaker, it will, in the linear case, affect very strongly the dynamic properties. Even the linear properties will shift the natural frequency, and maybe foremost, it will increase very, very strongly the damping value. So I would like still to further ask you to comment on the limitation that you may have if you have the task to validate a model.
Yeah.
For this, or how maybe in some cases this shaker structure interaction is not so severe. Maybe you have ideas what to do. So, for instance, what type of excitation you use, the base excitation was the shaker one, or maybe there are even other excitation mechanisms, and maybe where to place the exciter in order to somehow limit this influence.
Yeah, sure. So as you said, the actuator here has its own dynamical behavior. So it has a mass here of the center, there's a membrane, so there's some stiffness. And so if the resonance of the shaker here are in the same vicinity as the resonance of the structure, that can create a strong interaction. And so one way to ensure that you don't have such an interaction is to ensure that the frequencies that you're studying are very far from the dynamics of the actuator. And another thing that you can modify to remove these effects is linked the inertia of the mass of the actuator. If there is a high amplitude of motion, then the mass will act as an atom mass rigidly attached to a structure. And so if you are in such a case, you can move your shaker to a point where the displacement is not as high, so that this mass does not move as much and does not modify the dynamics of the structure. That is why, for instance, in this setup, I've put the shaker very close to the clamping so that the displacement was very, very, very small. And so you don't have a lot of motion inside the shaker.
Okay. There's one further question that I have that is regarding the architect continuation that you proposed. And among others, you looked into a system on the virtual experiment that has this piecewise linear stiffness, which I find quite challenging system because especially if you have relatively high contact stiffness, you can also have quite strong vibration behavior. For instance, also you might cycle vibrations one period to here, doubling and so on. Did you try to determine the limitations of your method in this regard, by choosing, for instance, much higher context thickness there?
I did, of course, play with the artificial parameter, the strength of the artificial nonlinear system is that you can show these parameters. And you are right that at certain points, the stiffness is so different that you have almost like right angles on the frequency response curve. And in this case, quasi-periodic motions and things like that begin to appear. And I think that's quasi-periodicity and nanocycle bifurcations would be the next thing. If this thesis lasted 4 more years, I think I would investigate quasi-periodic motion. But in this case here, these methods stabilize quasi-periodic motion. So quasi-periodic motion in open loop can be stabilized using, for instance, control-based continuation. It look like this, because it shifts. Like because if you look at the eigenvalues of this system when you do simplification, linearization, so that every eigenvalue is shifted to the left. And I suspect that something similar happens with quasi-periodic motion. That some flow exponents, etc., are stabilized. But that's still an open question. What exactly is the effect of control-based continuation in phase of loop on quasi-periodic motion?
Awesome. So in fact, you had a situation where quasi-periodic behavior occurred, and in open loop and close to you stabilize the periodic response instead, as corresponds to the unstable periodic behavior.
Yeah.
Okay, that's extremely interesting. Because I didn't find that in the thesis.
No, that's not. Actually, if I have to be honest, this was a thing being set up, and it is extremely dependent on the tightening of the screws. So this behavior, I found it by accident. And so once again, it's not a confirmed thing. It's just something that I observed. And so this could be to lead to further research. But unfortunately, I did not observe it back when I removed the beam and put it back together. The system is really, really sensitive. And even the isolat, I lost it at some points. So I could not observe back the quasi-periodic motion of this being open loop after demounting and remounting. That's something that I would like to investigate further.
Maybe one last question. What extensions, especially of this arcane classification, would you see in the future? Maybe except the part looking into quasi-periodic behavior. For instance, where you have a situation where you have more than one equation to deal with. Yeah.
In the context of applying this argument transformation process to multiple degrees of freedom system, what I would have liked to investigate further is variable steps. You could detect where you have interesting topological features like a resonance peak and so on by looking at how the phase lag changes, the slope of the phase lag. If you're really far away from resonance, the phase lag is almost constant, it's boring, and so you can increase the step continuation size. And that can increase the experiment time quite a lot, I think. And this is something that is done numerically as well. When you are finding multiple modes, you have variable steps. But now the second half of the question, you had an idea of something to investigate further.
In terms of if you, for some problems, I could imagine that you need more than one equation to deal with.
So in this case, if you want to identify frequency response curves with this system, process only one question. What kind of questions are you thinking about? Like on higher harmonics, maybe?
Yeah, actually, that this could be one application that might be possible.
Yeah.
Like again, for maybe higher harmonic cancellation, that also as you would also do some forms of the CMC. I'm not sure if you would think that this would be feasible, or you would say not for some reason that not be applicable.
I think it can be applicable. Now, the problem is that I talked already about is that the space, the input parameter space becomes really, really large with a huge number of dimensions. And so imagining an arc length going through all of these dimensions is a bit tricky to see, but you could imagine one arc length solving one equation, then another solving another equation, and you would find yourself like in an iterative process and trying to converge to the multi-dimensional equation that you want to solve. That is, I can think about it, but I don't know how you would confirm that you will converge using multiple arc length and multiple dimensions. So that's a really interesting. Yes, I think it would be possible, but I do not answer it. Thank you.
Okay, thank you. Thank you very much, Gaëtan. Very nice presentation. Thank you. It was very clear and understanding accessible. So the thesis, very good. So it was, like Monte said, a pleasure to be very, very I think you've got quite a few interesting contributions, especially I think what I keep in mind is the fact that you've significantly accelerated the implementation of those methods. And I think that that was a bottleneck in making them accessible to a great range of users. And now, going to the questions, at the very start of your thesis and also your presentation, you talk about unfolding. And I can see you smiling. I think one of the obviously key idea of continuation methods is to precisely deal with folding response curves. So how much is that really needed with some folding?
I guess it depends on the problem you are facing. If matters, then it can be relevant. For instance, when you have a nonlinear stiffness, strong nonlinear stiffness, where the peak is skewed and so on, it's important to tackle folding when you have fold bifurcations. When at some points in your experiments, if you change any input parameter, well, the response here cannot follow. So at this point here, you cannot. There's no input parameter that you can change to progress in either direction of the curve. That's only an example that you know very well. But if you are in such a case, in such a situation here, I think you have to tackle folding. Otherwise, some branches might be inaccessible. And one really important, example is the isolates. If you don't tackle fold bifurcations, you might miss isolate. If you don't tackle bifurcation, you might miss even curves that are connected. Imagine here, this peak went to the right, to the left, and then to the right. You could very well sweep everything without considering folding. You can identify everything except the highest resting center. So if you have a folded system, it's important to look at.
But I think I was making more the point that there's obviously the S-curve case, you can parameterize it differently, and in that case it's unfolded automatically. But I suppose that in your thesis you also mentioned unfolding just by, for instance, increasing the gains, and you can see that the curves gets unfolded. And it's linked to stability, isn't it? Because here, when you fold, you lose stability. So do you think that in general, this unfolding is required because we need to stabilize responses, or there are cases where things may still look folding, but they are still?
Yes, because there are examples of this, and I showed one in this case here. You have fold bifurcation. Every response is stable. So, I mean, we are like verb stability, of course, here and there, but all of these responses are stable. And so the fold are more geometric problem than a dynamical problem. So in this case here, I did not succeed in identifying this middle branch using phase lock loop only because I could not tackle the bifurcations here and there. If I went there, I jumped there. If I went there, I jumped there. So in this case, it's really important to get folding without having a problem with stability.
And so here, the problem of the red, remind me, was it?
Yeah, the red is only phase lock loop.
So here, the problem is not stability, it's just continuation. So for instance, if you were to use what you call action CVC,
Yes.
you would in principle be able to.
Yes, so I made a difference between excitation between action CVC, and the idea behind action CVC is to input like impose input parameters that did not exist before. Can I add something? So this is an example of an action CVC that you would use to identify, to solve the folding problem of an oscillator like I talked about. And if you only have these two input parameters, then the system is folded. And you would like an additional parameter that changes across the fold bifurcation. And so if you add some additional input parameters, it's more complicated, you have to juggle between them. But these additional input parameters can tackle folding in this case. And with action CVC, the idea is just, okay, I have a problem. I have a fold bifurcation. And so we try to find an input parameter that will allow me to move in this direction. Otherwise, I can't. And so you can imagine situations where you're not even considering oscillators, where you have a fold bifurcation, and you have to think about how can I input something in my system so that I can go in this forbidden direction. Like this here, this point should not be accessible in an open experiment because it's not part of the included circuit as well. But with the additional input parameter that you propose, then you can go outside this. That's why we talk about invasiveness. It's invasive when you are outside of the open response.
Just maybe in terms of the graphs that were in the thesis about continuation, we showed results of continuation and stability analysis. Just clarification, how did you produce those results, and especially when it comes to the high harmonics in the reference? What did you do about it?
So are you talking about chapter 2?
Yes, I think it's chapter 2, S-curves, differently.
Yes, well, the answer is very simple. The assumption is that the first harmonic is dominant. And so we actually ignore every higher harmonic. And so we can have, like in the thesis,
that was a single harmonic continuation.
Yes. Yes, we only consider the first harmonic. And then you can have instabilities in folds that emanate because of the superharmonic resonance. Like you talked in your review about folds that can appear in the control-based continuation S-curves have superharmonic resonances. If you include higher harmonics as additional parameters in your action CVC experiment, then you can tackle this fold bifurcation because you have an additional parameter.
I noticed in the stability analysis of the PLL, you didn't consider differential, and it was present in the chart. This wasn't. Yeah. So can you guide us? How does that affect your results of stability analysis?
Yeah. So these were the equations for the phase lock loop in the analysis. So we have here the theta, which represents the resonance frequency, the integration of the resonance frequency, and you only have the Kp here, the proportional damping, and then the Ki, the integral damping. Now, it's not forbidden to add a differential controller, and you can have a look at what it will do if we include it. So imagine you include a differential controller in your frequency, the frequency of your phase lock loop. Then you have the derivative of the estimation of the phase lock and the derivative of the phase lock target. Now, if we consider that the phase lock target is constant, this derivative is 0, right? And so we can simplify this term as simply this. And the derivative of the estimates of the phase lag, well, that's only the phase lag estimation method that you use. So it will really depend strongly on your phase lag estimation. In this analysis, the phase lag estimation was simply a low pass filter. And so you have immediately the expression of the low pass filter here that replaces the derivative of the phase lag estimation. So the cutoff frequency and the actual phase lag and the phase lag estimation. And so the consequence of this in the dynamics is that you have this new term here. And so by that here, the actual derivative of the phase lag will depend on itself. So I think you might have an instability because of that. Because, okay, if this is negative, then it's a positive effect, and the phi dot is damped more quickly, and the convergence time is shorter. But if this is positive, I don't know if this is possible, I haven't checked, then you are unstable. And then you have this kd omega LP times the estimation of the phase lag, and this is exactly the same term as this one with kp. And so the effect of the proportional gain will be diminished by the differential gain. Two effects. First, these dynamics will change depending on the sign k, either good or bad. And this is the opposite sign of kp, and so you will remove the effect of kp by adding. So these are the two effects of the thing. But that's I think it can benefit.
Sure. So, I mean, in the literature, I maybe not say you can comment on that, but I have the impression they use more frequently in
Yeah.
And there is a potential gain.
Yeah.
So yeah, that was cool. Useful or potentially
Can be useful, but I think you can achieve it using a proportion.
Also, I found interesting, I mean, in the analysis of show that essentially the sort of a sweet spot, the choice of game, it's actually not very far from the stability boundary. So, have you experienced in practice the sort of challenge in improving the performance of the PLN, and then you would essentially just go unstable, trying to.
I've been extremely big a lot of times. In the thesis, there is a lot of discussion about the comparison between ratification and synchronous modulation. And the difference is not as significant as the difference when we change the PI controller. So this minimum, this extremum that you talk about, the difference between this and something that is not optimal is not huge. It's like almost tiny. So the effort it would take to find the optimal controller, I don't think it's worth it. I think it's a lot of effort, it's not trial and error, because without knowing the nonlinearity of your system, you cannot find this optimal. And so you have to do trial and error. And it's not so much better than something is stable but not optimal. So, what was the question?
No, I got mine, so thank you. Now, I think you showed a very nice graph where you had your online CBC input and how it's much faster, but obviously you lose a bit of accuracy. Is there a way to, the problem is knowing whether it's too fast or not. And is there a way you can do that without having to have the answer?
Without diverging and risking to break everything. I did not find it. I did not find an efficient way of knowing if you are going to be unstable before you think.
I mean, no, just so if you go back to the slide, but where you had your online CBC effect.
you lose in terms of simply accuracy, simply because it is online, and you don't settle as much as you would in an offline manner. And so, yes, you've divided the time by 2, but the compromise is accuracy. So if now I've got specific requirements in terms of accuracy, how fast can I swim?
I think the best way to know that is to do an open loop experiment beforehand that will historically benefit only during the next weeks. I think a very easy way to observe this is to look at the Yes, good question. How do you know if you're inactive? That's basically the question.
Yes, that's the question. Without having to do the green.
Yes. That's the question. I guess it would be the same as when you do finite element analysis, see if you converge. So try a certain sweep, try a little slower, a little bit faster. And so you would have to do the experiments twice in a row to validate it. That's the thing I'm thinking about right now. But as next it serves.
Do you think there's analytically a way to sort of work out a setting time and if you converge?
Yeah, actually, if you excite your structure and then set the target to 0, you can see how fast you go to 0. And thanks to increased damping, you can have an idea on your damp. And so you could estimate the damping either starting from 0 and increasing suddenly the response and see how long it takes to go, or cutting the reference and cancelling the reference, see how long it takes to converge to 0. And from that estimation of the damping, you can estimate what is the acceptable rates for the input parameters. So that would be a good approach. Online.
Quite well, you still have time for one question.
Do you see any further improvement on this Fourier minded composition? So you've got these adaptive filters. Is there something even better than this, or you think that just flows the door there?
I would guess that there is definitely something better. What is better? This selection. One thing to know is that I only considered in the thesis I only wrote about the LMS algorithm for the adaptive filter. There are other algorithms that correct the weights, and I'm thinking about the RLS algorithm, for instance. And I think the RLS algorithm has faster convergence. I think it has higher performance in convergence. So if you're hunting after speed, you could consider another algorithm in your adaptive filter. Now to imagine another way of performing Fourier decomposition that would be better, that would require a lot of imagination because it's fast. So maybe I don't think about something right now. But for sure you can play with the algorithm.
And very, very last question. I mean, the last method, which I like very much, the PLM method, you end up having quite a few parameters to choose. Right? You have the say proportional, maybe derivative rule of CBC, then you have the filter, and then you have potentially 2 or 3 gains for the elements. How do you go about it in your experiment?
Yeah. First thing I do is tune the CBC. There's a central piece that ensures that we are unfolded and that we are stable. The PLL gain, the PLL can fulfill its full potential by just being a control feedback controller, traditional feedback controller. So you tune it like you would tune a linear PID controller, a linear system. So you want to there you could use a differential controller without any second thought, because you are just trying to reach the set point. So the PLL here can be really optimized using classical PID optimization methods. Then you can go down the PID controller, and that's not the stability is ensured by the CBC. So the PLL can really focus on reaching the phase lag target as fast as possible. And now for the adaptive filter, well, what I did is go with the critical move coefficients. So in the analysis, there's one which is the fastest, and usually it would be unstable. So I would decrease it until it's stable. So that's trial and error, basically. That's the CBC controller and the adaptive filter parameter. These are trial and error. The PLL that you can use traditional PID tube. Thank you. Thank you.
Yes, thank you very much. Congratulations from my side too. That's an excellent piece of work and slight feedback to start with. Very interesting topic, very manuscript, very nicely written in English. Smooth flow of ideas. As everybody mentioned, the combined theory and experiments, which is very nice to see. Also, the illustrations, would like to stress this. Very nice and richly illustrated. A nice object on its own. That's certainly a thesis written by an excellent mechanical engineer, I would argue. Very good comment of nonlinear dynamics. Clearly not a control engineer, as the presentation demonstrated it too. I also appreciate that you go to the Latin numbers every chapter. Very interesting. Closed loop experiments to me is also a big point. Much easier to do open loop experiments. Maybe the first things will be more complicated, but then when you close the loop and you close the experiments, that clearly makes your life harder. That's a thesis about control-based methods, and only about that, I would say. I felt a bit frustrated while reading the introduction and the conclusion. I was missing a bit the big picture, a bit the same as in this presentation, but that I also find very, very smooth, very nicely constructed. Maybe not fully accessible, I would argue, to a wide audience. In the thesis, clearly there are two parts. To me, there are first of all, the first 4 chapters where you get acquainted with the methods, and then the 2 last chapters full of maturity, independence, creativity. That was very nice to see. Maybe they arrived a bit too late, the ideas during the PhD. This was a bit lacking demonstration to be fully convinced about that, but they were quite convincing. So I'll try to have 5 questions, so we'll try to be very effective in asking them and answering. About the presentation first. And I was a bit surprised when I discovered the outline of the talk that you said on the same stage, PLS, CBC, and adaptive filtering. So is this what you consider as being your biggest contribution? Adaptive filtering is probably the best.
I think it's one of it's the door open. Yeah. I think adaptive finding the effect of adaptive filtering, improving the online Fourier decomposition, opened the door to faster and more creative control-based methods. And so I think it was a pivot point in the thesis to have this idea that could improve phase lock loop in the performance and control-based continuation in the continuation process. That's really what opened the door to these methods.
I have just a curiosity question, slide 31. That's a picture for setup. 31, yeah, several times. So yeah, you have a single shape in that experiment. Yes. Okay, so you both introduced the nonlinearity and perform the continuation within the same shape.
That's right. A lot of effort was put into ensuring that the signal that I input into the shaker was actually the force that lies here.
Yeah.
And that was to combine the excitation with the nonlinear force. If you don't have this, if you have different phases for different frequencies, you have a non-zero transfer, non-unitary transfer function, then the nonlinearity is completely distorted and the setup loses its power.
I see this setup with this artificial nonlinearity that you master and you know what you're providing to the system. I'm wondering why you have so many setups in the thesis. Why is this not sufficient? This not sufficient?
Well, this is a hybrid system between mechanical and numerical. And I feel like someone reading the thesis might wonder, okay, this is like the perfect setup. You can choose what you want and so on. But in real life, you have the nonlinearity that emanates from the system. And so would these methods work with a truly nonlinear system? That's why I'm thinking more system.
Okay, yeah, that was about the presentation. Then I have another question. At the beginning, you mentioned several times, looks that's not the full reality. We have a sine function, but we also have jumps with harmonics, let's face tags. We also have transients. That's something you don't talk much about. And I have this question. If you remember, if we take a linear system, simple degree of freedom system, so the simplest ever, we excite using a sine excitation. We have two parts in the resonance. We have the transient and the state. Do you remember which frequency you see in the transients?
The frequency in the transients is the resonance frequency.
It's the resonance frequency and it's steady state.
This is the excitation.
That's the force. So the natural frequencies of the transient, and in the steady state you just see the force. So if you ask students the question, which part of the resonance do you prefer to study natural frequencies? That's obviously the transient. And so so don't you find it counterintuitive to use steady state oscillations to study natural frequencies?
Well, depends how you work. And in this case, what really so the idea of stabilizing unstable response branches is, let's go with this. If you're only interested in resonance here, then transients would be a very nice way to do this. And there are multiple methods in the literature that use transients to go along the backbone curve naturally to have an estimate on the behavior of the model parameters depending on amplitude. And they use transients. But in this case here, this unstable branch here could lead to more branches, like the isola, for instance. And if you only consider resonance and not the side resonance, you can miss some response branches. And there are response branches that lead to other response branches. So to have full identification.
So regarding the method you have in mind that are using the transients, I guess this is open methods where it's provide initial conditions and look at the decay.
Yeah.
So I guess one of the, because this would remove this issue of shaper to structure interactions if we're just providing initial conditions. I'm wondering, I think one of the drawbacks of these methods is that when you provide your initial condition, then we know that the transient decays exponentially. So we don't have so many points at high level.
Yes.
So we don't really see the nonlinear resonance well.
And you can miss some features as well. If you have model interactions, you can switch
Yeah.
go around the tones and things.
So what about using transients in closed loop?
Well, the closed loop will modify the transients. So if you are like the closed loop influence the dynamics of the system. And if you're only interested in the dynamics of your structure, well, you will identify the dynamics of your closed loop. And that's a problem because you're only interested in the dynamics of your structure in open loop. So you could consider transients of the closed loop system if you're interested in the behavior of your closed loop system.
No, I'm really thinking about, so when you have the decay during the transient, it goes quite fast.
Yes.
Could we implement a controller that will allow us to decay very slowly along the transient to have the time to see the natural frequency?
Yeah. Very good idea. Here, we use control-based continuation to increase dynamically faster transients. But you could consider a controller, differential controller for control-based continuation with a negative differential gain, and then you will decrease the dynamic. So that's completely. I've not seen that in the literature. Trying to remove them from the structure, but that's completely possible, but then again, you have to make sure that you are observing the dynamics of the system and not observing the dynamics of your feedback loop with your negative difference.
Okay, and then I have another question. So that maybe take slide 16. I was very surprised to see the slide appearing there, slide 16.
Yeah.
So this is the big picture. I was expecting slide to be number 2. And but I'm wondering in the manuscript, right, that you have made an attempt, let's say in the PhD, to close the gap between academia and industry. And well, in one of your answers to Arthur's questions, you said if I would have 4 more years, I would look at precise periodicity. So that sounds again a bit like opposite statements. And honestly, when I see this slide, number 60, and this conclusion where you say I'm attempting to close the gap, it sounds a bit fake to me. And so the question is, if you would indeed go to the F16 aircraft, what's really missing in this method? Because I'm thinking about when you have multiple modes, maybe just the linear ingredients, multiple modes, highly damped modes, closely spaced modes, all those kinds of things, even just linear, weakly linear. Can you already deal with this?
I think with the alternate continuation methods, if you choose a step that is small enough, then you can have all the topology that is between the closely packed modes. So I think at least some of the challenges that you just cited, you could already tackle them with what is inside the thesis.
Yes. So you would say so you would be ready to apply this to the F16.
I think more has to be done on multiple subjects. One of the subjects is choosing the control cases to ensure that you are stable. Because if you are studying the F16, it's unacceptable to have an unstable control loop, to have divergence and things like that. And so I think that would be my number 1 priority. Work to ensure that you will never be unstable, that your gains will never be badly defined.
And if you go to industrialist method, could you, as a selling point, also say, look, just for linear identification, do you think this has an advantage over classical open loop techniques? I'm thinking about very sharp modes, so it's very difficult to identify the damping. Do you have an added value just for linear system identification too?
I would say yes. Yeah. So 2 points. First of all, so there are actually 2 methods that I showed here. The first one, with the alternate continuation, you are not doing a step in frequency, you are doing a step in length of the FRF. And so we will have, if the curves are vertical, well, you would have a step-by-step vertical, like numerical continuation. And that's a real strength, even if you have a linear system where the slope is really sharp. And then with the control-based spaced loop system, thanks to the feedback loop of the CBC, the control-based continuation, the damping is increased. And so if you want to have to identify a system with really low damping, this can reduce your experimental drastically because you will increase that.
That's also maybe a matter of the future for linear structures.
Yeah.
Let's conclude this. Thank you very much.
Thank you.
Thank you. So thank you, Gaëtan. I really enjoyed your presentation and your. So I'm not in the field, and I have to say that you did a very great work presenting different things. And so I was really urged, yeah, really to the manuscript. Really like it. And so I also have some questions about transients. So indeed, so when you go back to slide 15. So here I'm making a bit of parallelism with what we do in neuromotor engineering, because some of the techniques are the same. So you presented your control-based methods.
be the one. So the way you present it is that if you take the as an input the excitation of the two value and the output response amplitude, what you get is that you have jumps, and so you have unstable branches that can be identified. But if you use a controller to reverse that in a sense, right? Now with your controller, your input is the response amplitude, right? Because you control. And then what you look at is the output, which is the control output, is what you measure. And so in a sense, you invert it, the input and the output. That gives you your control, right? So that's what we do in the neuroscience as well using voltage clamp.
Yes.
But when you look at that, so what I want to, the first question I have is, so the excitation amplitude that goes out to the controller, what you're taking is steady state current.
Yes.
Right? Okay. So now let's say you do your experiments and then it takes some time for the response amplitude to reach steady state.
Yeah.
Does your controller reach steady state at the same time?
Answer would be yes.
Okay, but are you sure about that?
So we say that the definition of a controller reaching steady state is when its output reaches steady state, right?
So the control signal doesn't have to. So in a linear system, yes, but we are in a non-linear system, and non-linearities can also be dynamic, right?
Okay.
And so that can be a big part of the problem.
So are we talking about autonomous system
Well, it's not especially, but if you think about non-linearities going from components that have specific ranges in frequency or in time scale of population for instance, it means that you could have the non-linearity which is very big at some point in the frequency response, but it's fade away at sometimes.
Okay. So in this case, if your can you remind me the question you asked?
Yes. So maybe I could raise it a bit more mathematically.
Yeah.
So let's say this is your curve, right?
Yeah.
And so that's the bifurcation diagram, right? And it can be unfolded with an unfolding parameter. So you could have an unfolding parameter that unfolds. Let's say your unfolding parameter is also a variable in the system.
Okay.
Which means that bifurcation diagram will be unfolded dynamically all the time. And so you have different curves. When you apply a sign, after 1 second you have a curve, then after 10 seconds the curve changes. Yeah. So is it something that you see in these types of systems that you would care about?
This is not something that we observe in oscillators, mechanical oscillators. I guess if you have some kind of we'll say like viscosity in the nonlinearity or something like that. Pretty versatile. But in this thesis, I focused on nonlinearities that are defined as a relationship on the displacement of the velocity.
Yeah.
And so that means that, for instance, you have a power of your displacement. Your stiffness is the Q of displacement. You could imagine that the power changes in time, but that's not the case here. We are considering a system where whenever you apply your nonlinear function, if the input signal is always the same, then the output signal is always the same. This is the kind of nonlinearity that we are dealing with. So if you have a nonlinear function which is applied on some signals, if the signals stay the same, then the output of the nonlinear function stays the same as well. So I guess a simple way of seeing things is the nonlinearity is expressed like f of x dots, and not f of x dots, right? But in this case here, once these two signals have reached steady state in force, and the nonlinearity has reached steady state, that's not necessarily the case here. And these kind of nonlinearities have not worked with. So I don't know how they behave in the circumstances of control-based continuation with methods. Are we talking about the same thing?
So yeah, so the reason I'm asking that is that let's say we have that in your side. This is why I don't know if it exists here. Yeah. Let's say you have a nonlinearity which is transient. Yes. Right. You wouldn't see it in a steady state. So you then say this non-linearity, this jump exists.
Yeah.
And then you launch a satellite into space. If you see a transient sine wave at the same frequency, and then you see right?
Yeah.
And I think that you have the perfect tool to observe this with your control business. And now coming back to my first question, which was, do you think that, and have you seen, and do you think that the control signal is stabilized at the same time as your output? And if it doesn't, what does it mean?
In this case, I think in this study, it does. Now, I don't know if something similar exists in structural dynamics, in the same kind of nonlinearity, the transient nonlinearity that you are talking about. I don't think I know any of them. That does not mean that they don't exist, of course. But in this work, this was definitely not the case. So in this work, once the controller reaches steady states, it means that the output of the controller has also reached steady states, and that nothing changes anymore. Yeah.
So I didn't see any time courses of controller output in the. Do you have some?
Yes. Yeah, but because it was very far away.
Okay, that's okay.
I mean,
That's okay. That's okay.
If you look at the chapter 2, here this is the analytical exploration of CBC and PLL, and you can see in this actual time series of what I call the Van der Pol variables. So typically, the phase lag and amplitude of your signal will be changing through time. And in particular with PLL, you can see the outputs, that is the frequency. You can see how it changes. You can see how it converges to the expected value if your PLL is stable. So that in chapter 2, I think you will find a time series of controller audience.
Okay, thank you. Can you have cases coming back here? Can you have cases where it goes down after some time? So you have a first S-shaped application, but you have an inverse S-shaped application on the right.
You can have cases where the S-curve is non-monotonous. Now, as dramatically as you're coming down here, I cannot imagine something like that. But for instance, when you have superharmonic resonance, when a higher harmonic center into resonance, it can take a little bit of energy from the first harmonic. So there's one figure in the thesis where you can see an S-curve with a little loop in it, and that's when the third harmonic takes energy from the first harmonic. So locally, the first harmonic decreases in energy, and then that can input some faults in your control-based continuation, even if you have a very strong differential control difference.
So then there's no solution.
There is a solution, and we talked briefly about it, is finding a parameter to go on 4 bifurcations, and this parameter would be the amplitude of the third harmonic. And so you could consider what I call the action CBC experiments, where the third harmonic of the citation is not decided by your controller, but you input it manually, and then you have to iterate on it until you reach a response that is identical to the open loop response.
Okay, but I would be very interested to discuss about this. Very nice.
Yeah, it's something I'm not familiar with, so sorry about that. That's okay.
Yes. So, well, as a course of advice, I'm looking to really ask a question because I had a chance to discuss about the use of passive numbers. So, I just want here to give a comment regarding the presentation that I found extremely clear and impressively clear. I would say that people in the audience do not realize the enormous amount of high quality and complicated work which is behind. So this is a very nice demonstration also of the high level of maturity that you have accumulated to around these 4 years. So thank you very much for this presentation. And I think that at this stage I can stop my comments here. So, thank you.
Yes, maybe I will switch to French so that with your family understands the comments. So I'm apologizing for Malte, but it's a good occasion to practice. Tout d'abord, je voulais te féliciter. Tout le monde du jury, je pense que tu as fait un travail exceptionnel. Bon, quand je t'ai proposé le sujet, je ne pensais pas qu'on arriverait à tant de nouvelles idées, tant de développement, tant de réalisations pratiques. Donc moi, j'ai 3 peut-être mots-clés pour caractériser ton travail et peut-être ta personne. C'est tout d'abord, ce qui est intéressant, c'est que je les ai mis avant, évidemment, mais on les a entendus. En commentaire des autres membres du jury, c'est la créativité. Donc je pense que tu es quelqu'un qui est extrêmement créatif. Donc évidemment, pour une thèse de doctorat, c'est un atout indéniable. Alors évidemment, la créativité parfois, quand il y en a trop, alors je ne vais pas dire qu'il y en a eu trop dans ton cas, mais parfois la créativité peut donner lieu à tellement d'idées, tellement de choses à faire qu'on peut en avoir de la frustration. Mais je pense que voilà, la réalisation de ta thèse après 4 ans, tu as réussi à bien gérer ta créativité, ça bravo. Et avec des idées, je pense que maintenant on a besoin de 2 ou 3 doctorants pour en fait finaliser ton travail, ce qui est plutôt très positif comme commentaire. Mettre en avant aussi ton efficacité, parce que je me souviens qu'on a eu des discussions où je te demandais de faire quelque chose et 2 jours après, tu arrivais avec le setup expérimental, voilà, je l'ai fait. Vraiment très efficace, hein, donc vraiment impressionnant de pouvoir réagir aussi vite. Donc, tu aimes bien les défis. Quand on te pose un petit défi, une petite question, on voit que tu sais aller à l'essentiel. Et finalement, pour ton enthousiasme, parce que voilà, évidemment, le doctorat, c'est toujours une longue période avec des hauts, des bas, et je pense que ton enthousiasme et ta passion pour ce que tu fais t'ont permis de passer les obstacles qui se retrouvent naturellement sur le chemin de la réussite. Et donc, l'enthousiasme aussi que tu m'as communiqué, Christophe, pour avoir des réunions avec toi, c'était toujours très intéressant, toujours fascinant. Donc voilà, je pense que, bon, je ne vais pas être trop long parce que le temps passe. Mais voilà, encore merci pour ton travail. Et je pense que tu peux vraiment en être fier. Merci.
On peut suivre des questions du public. So if you have any question in French or in English. Personally, we have just one question. Okay, we didn't talk about sensors. So you can use different types of sensors and you did. This is something several years. Regarding the method that you have developed, we have some recommendations about the choice of the sensor. Is one type of sensor more appropriate to one of the methods, or is it not so particular?
One important component is noise and how noise amplifies certain frequencies. For instance, when you use control-based continuation, the stabilization comes from the differential controller that adds damping to the system. And of course, the differential controller will amplify high-frequency noise really much. So if you have a sensor with some high-frequency noise, it will be amplified by the differential controller. You might have some trouble here. But otherwise, yes, and the second comment, if you are using accelerometer and integrating their values to have the displacement of the velocity, the problem that can arise is that because in this system, this is not traditional feedback control. You have an oscillating signal here at the input and an oscillating signal here at the output. That means that if you are using, for instance, proportional controller or even worse, an integral controller, and you have a set point error here, then you will have a huge force that will be applied that can grow through time as well. So if you are integrating the signal of your sensor to feed it back, we have to make sure that there's no set point error.
Otherwise, your excitation here might get very large very fast.
L'Université de Liège est membre de l'Académie universitaire Wallonie-Bruxelles. Le décret du 7 novembre 2013 définissant le paysage de l'enseignement supérieur et l'organisation académique des études. Président, secrétaire et membre du jury chargé de conférer le grade académique concerné, déclarons que Gaëtan Abeloos obtient en l'année académique 2022-2023 le grade académique de docteur en sciences de l'ingénieur et technologie, après avoir défendu publiquement une thèse intitulée Control-Based Methods for the Identification of Nonlinear Structures. En foi de loi, nous nous délivrons le présent diplôme, attestant en même temps que les prescriptions légales relatives aux conditions d'accès au programme, à la durée des études et à la publicité des examens ont été observées. Nos félicitations.